Bismillah ar-Rahman ar-Rahim. This video is about this inequality regarding the Q function, which is the complementary CDF of a standard Gaussian random variable. Q of small x is the probability that random variable big X, which is a standard Gaussian random variable, so it has a mean of 0 and a variance of 1. Q of x is the probability that random variable big X is strictly greater than small x. Using the Gaussian PDF, Q of x can be written as this integral 1 over square root 2 pi integral from small x to infinity e to the minus 1/2 u squared du. There are many useful inequalities, lower bounds and upper bounds related to the Q function. But what we need here is another integral representation for the Q function and the square of the Q function. The Q function is given by this integral here. And this integral is equal to 1 because it is the integral of the PDF of a standard Gaussian random variable. If we multiply these together, we get the Q function, Q of x, equal to 1 over 2 pi, and then we have the double integral of e to the minus 1/2 u squared plus v squared. V is from minus infinity to infinity, and u is from x to infinity. This is the domain of integration in the uv plane. Let's now do a change of variables. Let u be equal to r cosine phi and v equal to r sine phi. In other words, we do a change from rectangular coordinates to polar coordinates. U squared plus v squared, this is equal to r squared. Du dv is r dr d phi. What about the limits of integration? This is the region that we are integrating over. Given phi, and given that this distance is equal to x, then this length here is equal to x over cosine phi or x sec phi. The variable r, which represents the distance to the origin, starts from x sec phi all the way to infinity. What about phi itself? Phi is from minus pi over 2 all the way to pi over 2. We can evaluate the inner integral because this is minus integral from x sec phi to infinity de to the minus half r squared. So this is e to the minus half r squared, x sec phi, and infinity. In the limit as r tends to infinity, this approaches 0, and if r tends to x sec phi, we get e to the minus half x squared sec phi squared. The integrand is an even function in phi, and so we can write it as an integral from 0 to pi over 2, and we multiply by 2. Then we can change phi to pi over 2 minus phi. Or if we do things in slow motion, let theta be equal to pi over 2 minus phi. We have 1 over pi. When phi is 0, theta is pi over 2. When phi is pi over 2, theta is 0. The integrand becomes e to the minus 1/2 x squared, 1 over the square of cosine pi over 2 minus theta, and d phi is minus d theta. This minus sign can be used to have the integral from 0 to pi over 2 d theta. The integrand is e to the minus half x squared divided by sine theta squared, because cosine pi over 2 minus theta is equal to sine theta. This is another useful integral representation of Q of x. On the left-hand side of the desired inequality, we have the square of the Q function. So let's try to do something similar to Q squared. The integral of the Gaussian PDF, like any PDF, is equal to 1. Let's split this integral into 3 integrals, from minus infinity to minus small x, and x is positive, and then from minus x to x, and then from x to infinity. By definition, the integral here from x to infinity will give us Q of x. And by symmetry, the integral from minus infinity to minus x will also give us Q of x. Thus, the integration of the Gaussian PDF from minus x to x plus 2 times Q of x, this is equal to 1. This integral here is equal to 1 minus 2Q of x. Let's square both sides. 1 over square root 2 pi becomes 1 over 2 pi. The integral becomes a double integral in which we integrate e to the minus half u squared plus v squared over the origin-centered square of side length 2x. As above, we can do a change from rectangular to polar coordinates. Du dv becomes r dr d phi. The integrand is e to the minus 1/2 r squared. What about the limits of integration? Note that due to symmetry, this integral can be carried out over this triangle, and then we can multiply the result by 8. Over this triangle, if we fix phi, and since this distance is equal to x, then this length here is equal to x divided by cosine phi, which means that the variable r goes from 0 to x sec phi. The angle phi is in the range from 0 to pi over 4. We can carry out the inner integral as we did above. Now we get 1 minus e to the minus half x squared sec phi squared. If we split the integrand, this is equal to the integral of 1 from 0 to pi over 4, that's pi over 4 times 4 over pi, that's 1, minus 4 over pi, the integral from 0 to pi over 4, e to the minus half x squared sec phi squared d phi. Let's move to the left-hand side and expand the square. We have 1 minus 4 q of x plus 4q of x squared. This one goes away with that one. We can move this minus 4 q of x to the other side and divide by 4. Doing this, we get that the square of the q function is q of x minus this term here divided by 4. We have this representation for the q function, so let's make use of it to write down q squared of x as the difference between these two integrals. The integrand is exactly the same. Here we are integrating from 0 to pi over 2. In this integral, we are integrating from 0 to pi over 4. We can combine these two integrals and have one integral from pi over 4 to pi over 2. Now let theta be equal to pi over 2 minus phi. When phi is pi over 4, theta is pi over 4. When phi is pi over 2, theta is equal to 0. d phi is minus d theta. And the integrand is e to the minus 1/2 x squared divided by cosine pi over 2 minus theta squared. We can use this minus sign and have our integral from 0 to pi over 4. Cosine pi over 2 minus theta is sine theta. And if we rewrite our integral using the variable phi, the integrand becomes e to the minus x squared over 2 sine squared phi. We have obtained two integral representations for q of x and q squared of x. Both of them have this factor 1 over pi. Both of them involve the same integrand, but the integral for q of x is from 0 to pi over 2, and the integral for q of x squared is from 0 to pi over 4. Let's take the difference between the two sides of the desired inequality and represent q and q squared using those integrals. Q of square root 8 times x is this integral here, and x squared is replaced by 8x squared. This becomes 2 over pi, and then the integral from 0 to pi over 4, e to the minus 2x squared over 2 sine phi squared. Write down this integral in terms of the dummy variable of integration theta, and then let's do the change of variables. Phi is equal to theta over 2. When theta is equal to 0, phi is equal to 0. When theta is equal to pi over 2, phi is equal to pi over 4. d theta is equal to 2 d phi, and the integrand becomes e to the minus 8x squared over 2 sine of 2 phi squared. When we do this substitution, we are able now to combine these two integrals, as both of them have this external factor 2 over pi, and both of them are from 0 to pi over 4. The difference between these two terms, which are the sides of our desired inequality, is given by this integral here. We are done if we can show that this integral is greater than or equal to 0. Is this the case? If we take the angle phi from 0 to pi over 4, cosine squared phi is positive and is less than 1. This means that 4 sine squared phi times 1 is superior to 4 sine squared phi times cosine squared phi. This is 2 sine phi cosine phi all squared, and this is sine of 2 phi. If we take the reciprocal of both sides, we have 1 over 4 sine squared phi is strictly less than 1 over the square of sine 2 phi. This inequality remains the same if we multiply both sides by 4x squared when x is strictly positive. This becomes x squared over sine phi squared less than 4x squared over the square of sine 2 phi. Multiply both sides of this inequality by minus 1, and this will cause reversal in the inequality. Minus x squared over sine phi squared is strictly greater than minus 4x squared over sine squared 2 phi. And x is non-negative. If x is 0, then we get equality. The exponential function is strictly increasing, so this inequality is the same if we exponentiate both sides. This is exactly what we need. This exponential is greater than or equal to that one. So this minus this is greater than or equal to 0, and the integral of the non-negative function is non-negative. This difference here is greater than or equal to 0, thereby indicating that our desired inequality is indeed true for every non-negative x.